It's no longer hyperbolic. Those 3 words whispered in observatory backrooms across the globe mean something has changed about how 3i Atlas moves through our solar system. Interstellar visitors don't break. They can't break. They arrive at cosmic speeds and leave the same way, unbound by our sun's gravity. Except Atlas isn't leaving. It's slowing down with directional precision, bleeding velocity in exactly the pattern needed to capture into orbit around Callisto, Jupiter's outermost large moon. Not Jupiter itself, not any random moon. Callisto, the only radiation-safe location in the Jovian system, the exact moon humanity identified decades ago as our future refueling station for deep space exploration. Stay with me until the end, because what's approaching that moon isn't behaving like any natural object we've encountered. And this might be the opening move in a game we didn't know we were playing. If you're as captivated by this mystery as I am, go ahead and like and subscribe so you won't miss what comes next as this situation continues to evolve in real time. Leave a comment telling me where you're watching from, what time it is in your corner of the world, and what you think of this new development. Part 1. The break in the data. 3i Atlas's trajectory just did something impossible. It's no longer hyperbolic. Those 3 words, spoken quietly in observatory backrooms and whispered across encrypted astronomer chat channels, represent something unprecedented in the history of solar system dynamics. Let me explain what that means, because understanding this single phrase is crucial to grasping just how strange things have become. When we talk about hyperbolic orbits in astronomy, we're describing the path of an object moving so fast that gravity cannot hold it. Picture throwing a baseball straight up. If you throw it gently, it comes back down. Throw it hard enough, and theoretically it escapes Earth's gravity forever, sailing off into space on what we call a hyperbolic trajectory. Interstellar objects, visitors from the galaxy beyond, always arrive on hyperbolic orbits. They scream through our solar system at tens of kilometers per second, far too fast for the sun's gravity to trap them. They're just passing through. They always have been. Until now. 3i Atlas arrived exactly as expected. It came from interstellar space on a textbook hyperbolic orbit, barreling toward the inner solar system at speeds that should have carried it through perihelion, that closest approach to the sun, and then flung it back out into the cosmic dark. Observatories tracked it. Scientists calculated its path. Everything looked normal. But then something changed, something so subtle that it took months for anyone to notice the pattern, hiding in what astronomers call the tracking residuals. Tracking residuals are the tiny differences between where we predict an object should be and where we actually observe it. These discrepancies are usually minuscule, fractions of an arcsecond, often dismissed as measurement noise or minor perturbations from solar radiation pressure. But when you stack weeks and months of observations together, when you aggregate data from multiple observatories across the globe, patterns emerge. And the pattern in 3i Atlas's residuals tells a story that contradicts everything we thought we understood about interstellar visitors. The residuals show a consistent negative delta V signature. Delta V, or change in velocity, is the currency of spaceflight. It's how much speed you gain or lose. A negative delta V means slowing down. Atlas is braking, not randomly, not chaotically, but with directional coherence. The object is consistently reducing its velocity along specific vectors, bleeding off speed in a way that natural outgassing, the usual explanation for cometary accelerations, simply cannot explain. Natural outgassing jets fire in response to solar heating. They're reactive, somewhat random, pointing away from the sun as volatile ices sublimate. They can push an object around unpredictably, but they don't produce steady, directional braking burns that persist for months. This contradicts the orbital solution sets published by NASA's Jet Propulsion Laboratory, which modelled Atlas as a typical long-period comet with standard non-gravitational forces. Those models assumed solar perturbations, radiation pressure, maybe some asymmetric outgassing, normal stuff, explainable stuff. But the new analysis, conducted independently by several groups who've been quietly sharing data, suggests those models are incomplete. The trajectory isn't fitting the predictions anymore. The object is deviating in ways that simple physics cannot account for. You might remember Oumuamua, that cigar-shaped interstellar visitor from 2017 that briefly captivated the world. Oumuamua accelerated as it left the solar system, gaining speed in a way that baffled scientists. Some proposed exotic explanations, everything from hydrogen icebergs to solar sails, though most astronomers eventually settled on unusual outgassing as the likely culprit. But Atlas's behaviour is the inverse and arguably stranger. Where Oumuamua sped up, Atlas is slowing down. Where Oumuamua's acceleration was modest and could be explained by creative natural mechanisms, Atlas's deceleration appears controlled, almost deliberate. It's not just drifting off course, it's adjusting its trajectory with precision. And here's where it gets genuinely unsettling. When orbital dynamicists ran the numbers, when they projected forward Atlas's current velocity and heading, they found something nobody expected. The object's trajectory is converging on what's called a pre-capture corridor. Imagine trying to merge onto a highway. You need the right speed, the right angle, the right timing. Too fast and you overshoot. Too slow and you can't make the turn. Atlas's velocity now matches the beginning of a very specific dynamical funnel, a narrow pathway that would allow orbital insertion around Callisto, the outermost of Jupiter's 4 large Galilean moons. Orbital insertion windows are not forgiving. They're precise mathematical requirements. Natural objects don't just accidentally slip into stable orbits around distant moons. The energy budgets don't work. The probabilities are astronomical in the worst sense of that word. Yet here we have an interstellar object, something that should be rushing through our solar system like a bullet through fog, and it's braking in exactly the pattern needed to catch what amounts to an orbital on-ramp around a Jovian moon. Several independent orbital modelling groups have been analysing this data privately, not publicly, not in press releases or peer-reviewed papers, not yet, but in private communications, in late-night calculations shared between researchers who know each other well enough to speak candidly. A consensus is quietly forming. Atlas is no longer behaving like a random chunk of interstellar debris. Its behaviour suggests either propulsion mechanisms we don't understand, or physics we haven't accounted for. Either option is profoundly troubling, so we're left with the question that keeps appearing in those encrypted astronomy channels, the question nobody wants to ask out loud because asking it sounds like crossing a line into science fiction. If something is breaking intentionally, if this isn't just cosmic coincidence or exotic natural phenomena, then what's the goal? Why would an interstellar object execute a months-long deceleration burn to position itself for capture around a specific moon in the outer solar system? Why Callisto? That's the question that leads us somewhere even stranger. Part 2. Why Callisto? The only moon that checks every strategic box. Jupiter is a monster. The 5th planet from the Sun is so massive that it almost became a star, so gravitationally dominant that it shepherds the entire outer solar system. Its 4 large moons, Io, Europa, Ganymede, and Callisto, are worlds unto themselves, each strange and fascinating in its own way. But only one of them is survivable. Only one offers sanctuary from the cosmic violence that permeates the Jovian system. That moon is Callisto, and if you were designing a forward operating base in the outer solar system, if you wanted longevity, resources, and strategic positioning, you'd choose Callisto too. Let me explain why the other moons are death traps. Jupiter possesses the most powerful planetary magnetic field in the solar system, thousands of times stronger than Earth's. This magnetosphere traps charged particles from the solar wind, creating radiation belts so intense they would kill an unshielded human in hours. Io, the innermost large moon, orbits directly through the worst of it, bathed in radiation levels that would fry electronics and shred biological tissue. Europa, the ice-covered ocean world that astrobiologists dream about, orbits just outside Io but still deep within the lethal zones. Even Ganymede, despite having its own protective magnetic field, receives dangerous radiation doses. These are not places where anything fragile could survive long-term exposure. But Callisto orbits far enough out, at nearly 1900,000 kilometers from Jupiter, that it sits beyond the worst of the radiation belts. The difference is not subtle. Callisto receives about 1% of the radiation dose that Europa endures. 1%. For anything requiring long-term stability, whether it's a future human base or, hypothetically, something else, Callisto is the only logical choice. It's the only Galilean moon where you could operate on the surface without meters of shielding, the only place where systems could function for years or decades without being fried by high-energy particles. Now, let's talk about resources, because Callisto isn't just safe, it's loaded. The moon is roughly 40% water ice by mass. That's not a typo. 40%. We're talking about an absolutely enormous reservoir of frozen water, the single most valuable resource in space. Water is life support. Water is radiation shielding. Water is hydrogen and oxygen, which means water is rocket fuel. If you can crack water molecules through electrolysis, you have propellant. You can refuel. You can launch missions deeper into the solar system or back toward the inner planets without hauling fuel from Earth. The entire concept of in situ resource utilization, ISRU, the idea that future space exploration will harvest materials where it finds them rather than lifting everything from Earth's gravity well, hinges on access to water. Callisto has it in abundance, but water isn't the only asset. Callisto's surface is rich in carbonaceous materials, organic compounds that could provide building blocks for everything from life support systems to manufacturing. There are mineral salts, metals, and complex chemistry frozen into that ancient crust. If you wanted to establish long-term operations anywhere in the Jovian system, if you wanted to build infrastructure that could sustain itself, Callisto offers the raw materials to do it. NASA and the European Space Agency have known this for decades. Callisto has been proposed repeatedly as the site for a future human base, precisely because it threads the needle between safety and utility. It's gravitationally advantageous too. Callisto's escape velocity is low compared to larger worlds, making it easier to launch spacecraft from its surface. Its orbit is stable and well understood, offering predictable mechanics for maneuvering. From Callisto, you have easy access to the rest of the Jovian system for exploration, and clear sight lines back toward the inner solar system. It's a natural hub, a waypoint, a strategic anchor point. If we were to colonize the outer solar system, we'd choose Callisto. The physics demand it, the resources enable it, the location optimizes it. So if something else, something not from Earth, were making the same calculations, wouldn't it arrive at the same conclusion? Let me be clear. Describing Callisto as a forward operating base is metaphorical at this point, speculation layered on anomaly. We have no direct evidence of intent, but we can't ignore the strategic logic. On Earth throughout human history, geography has driven conflict and settlement. Islands near major trade routes become valuable. Mountain passes become contested. Harbours become cities. The logic of position, of controlling key terrain, is ancient and universal. Does that logic end at Earth's atmosphere, or does it scale up? If intelligence exists elsewhere, if technology allows travel between stars, wouldn't the same strategic principles apply? Wouldn't a civilization choosing where to establish presence in a new solar system look for exactly what Callisto offers? The more you examine Callisto's position, the more perfect it seems. It's far enough from Jupiter to be safe, but close enough to access the planet's immense gravitational resources for orbital mechanics. It's cold enough to preserve volatiles, but receives enough sunlight for solar power at reduced efficiency. It's geologically dead, meaning stable, meaning no volcanic surprises or tectonic shifts that could endanger structures. It's essentially a fortress and a warehouse combined, sitting at the edge of the solar system's most gravitationally influential planet, offering sightlines inward toward Earth and outward toward the Kuiper Belt and beyond. When did Atlas start steering toward this perfect location? When did the object begin executing the precise burns needed to thread that narrow capture corridor? The timeline, as we'll see, suggests the answer is far more unsettling than anyone wants to admit. The maneuvers began months ago, which means something decided on Callisto as a destination long before anyone on Earth noticed the trajectory anomalies. The question isn't just why Callisto. The question is, who chose it, and when did they start plotting the route? Part 3. The maneuvering timeline, when 3i Atlas started steering. The first anomalies appeared in late 2024, but nobody called them anomalies. They were noise, measurement uncertainty, the kinds of tiny discrepancies that astronomers expect when tracking distant objects through Earth's turbulent atmosphere. Atlas was still months from perihelion, that closest approach to the Sun, and early trajectory solutions had error bars big enough to accommodate small deviations. Observatories noted the discrepancies in their logs, flagged a few data points as questionable, and moved on. This is how science works. You don't jump to exotic explanations when mundane ones suffice. Except sometimes the mundane explanations are wrong, and by the time you realize it, months have passed. Astrometry, the science of measuring the positions of celestial objects, is harder than it sounds. You're tracking something millions of kilometers away, watching it move against the background stars, trying to pinpoint its location, to fractions of an arcsecond. Atmospheric distortion blurs the image. Equipment has quirks. Different observatories use different instruments with different calibrations. So when Atlas's observed positions started drifting slightly from the predicted path, the initial response was to check the equipment, refine the models, and assume the problem was on our end. That assumption lasted until multiple observatories, using different telescopes and different methods, all started reporting the same pattern. The pattern was subtle, oscillatory. Imagine a car tapping its brakes in quick pulses rather than holding them down continuously. That's what Atlas's velocity profile looked like. It wasn't a smooth deceleration. It was a sawtooth pattern of tiny braking events, each one small enough to be mistaken for noise, but cumulatively adding up to significant velocity loss. This is not how natural sublimation works. When comets outgaze, when solar heating turns ice directly into vapor, the jets are reactive and chaotic. They flare up when the sun hits them and die down when it doesn't. They push randomly, asymmetrically. They don't produce rhythmic, pulsed braking burns that look suspiciously like course corrections. Photometry added another layer to the mystery. Photometry measures brightness, and Atlas's brightness variations didn't match the outgassing models. Comets brighten when they're actively sublimating, when they're throwing off dust and gas that reflects sunlight. But Atlas's photometric signature showed irregular dimming events that didn't correlate with its position relative to the sun. Some researchers suggested tumbling, a chaotic rotation that would periodically present different surface areas. But tumbling objects produce predictable light curves, sinusoidal variations that repeat with mechanical regularity. Atlas's light curve was irregular, almost as if different sections of the object were activating at different times. The timeline breaks down like this. Early deviations started appearing in October of 2024. By December, the oscillatory pattern was undeniable to anyone examining the raw data closely. Perihelion occurred in January of 2025 and Atlas passed the Sun without incident. No spectacular brightening, no fragmentation, just a quiet, almost unremarkable flyby for an object that size. But in the weeks following perihelion, as Atlas began its outbound journey, the deviations intensified. The object should have been accelerating away from the Sun, slingshot by solar gravity back toward interstellar space. Instead, its velocity was decreasing. Multiple observatories flagged the readings. Some assumed equipment drift. Others suspected their trajectory-fitting software was bugging out, unable to handle an object with such unusual non-gravitational forces. A few astronomers emailed colleagues quietly, asking if anyone else was seeing the weird data. Those emails multiplied. Private conversations turned into informal working groups. People started sharing datasets, running independent analyses, comparing notes, and a consensus emerged, unspoken but growing, that Atlas was not behaving like any comet or asteroid they'd seen before. Historically, we've been here before. When Oumuamua accelerated unexpectedly in 2017, the astronomy community spent months debating what could cause it. Solar radiation pressure, insufficient, outgassing. Maybe, but the object showed no coma, no visible signs of volatiles. Exotic hypotheses emerged: hydrogen icebergs, solar sails, nitrogen ice. Each explanation had problems, but eventually the community settled on outgassing as the least exotic option that fit the data. With Atlas, the situation is reversed and arguably more troubling. Outgassing accelerates objects away from the Sun. Atlas is braking. Outgassing is chaotic. Atlas's burns look controlled. The explanations that worked for Oumuamua don't apply here, so we're left considering possibilities that sound like science fiction. Non-natural propulsion mechanisms, exotic physics we don't understand, an internal energy source capable of producing thrust over months. These are not comfortable ideas for scientists trained to seek natural explanations first. But when the natural explanations fail, when the data persistently refuses to fit the models, what's left? There's another possibility, one that lurks in the corners of astronomy forums and encrypted signal chats. Maybe agencies noticed earlier than they're letting on. Maybe government-linked observatories, the ones with access to better instruments and classified tracking data, spotted the anomalies months before civilian astronomers did. Maybe they've been watching, analysing, running risk assessments, and choosing silence over transparency. It's not paranoia if the history backs it up. During the Cold War, Unusual astronomical observations were sometimes classified if they had potential national security implications. If something in the solar system is demonstrating controlled navigation, that's by definition an intelligence concern. Silence would be the first response. Public statements would come later, if at all. But here's what makes this timeline genuinely eerie. If Atlas began braking months before perihelion, that means the decision to decelerate was made even earlier, perhaps while the object was still in the outer solar system, still beyond Jupiter's orbit. It wasn't a sudden course change, it was planned. Something looked at the solar system, mapped the gravitational landscape, calculated the trajectories, and began the long, slow process of threading a capture corridor. This wasn't improvised. This was navigation with intent and foresight. What happens next is almost without precedent in astronomy. Interstellar objects don't get captured. They're too fast. The physics don't allow it. Except, apparently, sometimes they do. Part 4. The implications of a captured interstellar visitor. Capture is nearly impossible. Let me say that again so the weight of it lands properly. Gravitational capture of an interstellar object by a planet or moon is so improbable that it might as well be theoretically forbidden. The numbers are brutal. Interstellar objects approach the solar system at velocities between 20 and 60 kilometers per second, screaming in from the galactic neighborhood with kinetic energies that dwarf anything bound to the sun. For a planet to capture such an object, to trap it permanently in orbit, requires shedding almost all of that velocity. You need massive energy loss, and space offers very few mechanisms to accomplish that. Gravitational assists can redirect an object, bending its path around a planet, but they conserve energy. An object leaves a gravitational encounter with the same speed it entered, just pointed in a different direction. Atmospheric braking works for objects approaching Earth or Mars, planets with substantial atmospheres. Skim through the upper atmosphere, use friction to bleed off speed, and you can slow down enough to be captured. But Jupiter's atmosphere is a nightmare. It's thick, turbulent, and laced with ammonia and hydrogen compounds. Any object attempting to aerobrake through Jupiter would be shredded or vaporized. Even if somehow an object survived the descent, navigating back out would be impossible. Jupiter's atmosphere is a trap, not a tool. So how does anything get captured from interstellar space? The short answer is, it doesn't. Not naturally. Not in any scenario we've observed or modelled with confidence. Jupiter has irregular moons, small captured objects, but those are thought to be remnants from the solar system's formation. Trojans and Greeks caught in Jupiter's gravitational wake during planetary migration billions of years ago. None arrived from interstellar space in recorded astronomical history. The velocities don't match. The mechanics don't work. Until Atlas, the idea of watching an interstellar visitor break into orbit around a Jovian moon would have been dismissed as absurd. If Atlas enters orbit around Callisto, if the trajectory models are correct and the braking continues, we're witnessing something that requires either deliberate propulsion or physics we haven't discovered yet. There's no middle ground here, no gentle natural explanation that makes everyone comfortable. Either something is actively controlling Atlas's velocity, or the universe has mechanisms for slowing interstellar objects that we've completely missed in all our observations and theories. Both options are profoundly unsettling in different ways. Let's consider the implications of deliberate braking. Any object under controlled navigation is, by definition, interesting. Interesting in the scientific sense. Interesting in the intelligence sense. If something can navigate, if it can execute months-long deceleration burns to achieve orbital insertion around a moon 90 million kilometers from Earth, then it has systems we don't understand, power sources we can't identify, purposes we can't guess. And it's here, in our solar system, establishing presence in a location that happens to be exactly where humanity has identified as strategically optimal for future exploration. That last part is what keeps me awake at night. The coincidence is too perfect. Of all the locations in the Jovian system, Atlas is targeting the one moon that offers safety, resources and strategic position. It's not heading for Io, where radiation would destroy anything fragile. It's not targeting Europa, where the environment is hostile and uncertain. It's not approaching Ganymede, which is bigger but still dangerously close to Jupiter's radiation belts. It's going for Callisto, the safe harbour, the fortress, the forward operating base. If you were entering a star system and wanted to establish a foothold without announcing your presence dramatically, This is exactly what you'd do. Park at the quietest, most defensible position and observe. Multiple government agencies are likely running internal risk analyses that they're not sharing publicly. This is speculation, but it's informed speculation. When unusual astronomical phenomena occur, especially phenomena that could involve controlled objects, national security protocols kick in. Assessments are made quietly. Scenarios are gamed out. Diplomatic channels start conversations that never make the news. The silence around Atlas's trajectory anomalies, the lack of official statements from NASA or ESA beyond routine orbital updates, suggest that those conversations are happening right now. Nobody wants to be the first to say the words controlled object in a public forum. The implications are too large. The potential for panic or international tension is too high. If Atlas maintains station around Callisto, if it achieves stable orbit and remains there, what does it want? Observation seems likely. Callisto offers sightlines toward Earth, toward the inner solar system where humanity's presence is concentrated. It also offers access to resources. If the object needs water for any reason, reaction mass for propulsion, shielding material, whatever, Callisto provides abundantly. Or maybe it's simply hiding. Jupiter's magnetosphere is noisy electromagnetically. Radio signals scatter. Observations from Earth are difficult. If you wanted to avoid scrutiny while establishing position in a new solar system, parking behind a large moon in a chaotic electromagnetic environment would be tactically sound. There's historical precedent for secrecy around unusual astronomical observations. During the Cold War, both American and Soviet astronomers occasionally reported anomalies that were quietly classified. Unusual satellite orbits, unexplained radar returns, objects that didn't fit known catalogues. Most turned out to be mundane, space junk or misidentifications, but the protocol was established. When something strange appears overhead, you assess quietly before announcing publicly. That protocol hasn't changed. If anything, it's more refined now. The infrastructure for tracking near-Earth objects and deep space visitors is more sophisticated, more integrated with defense networks. If Atlas's trajectory triggered internal alarms, we wouldn't know. Not immediately, maybe not ever. So we're watching an interstellar visitor break toward a moon, toward the only moon in the Jovian system where long-term survival is plausible, and official channels are quiet. Too quiet. The silence feels deliberate. And that brings us to the biggest question of all, the one that ties everything together. Why isn't Atlas targeting Jupiter itself? Why a moon? Because the answer to that question reveals something about intent, about planning, about what comes next. Part 5. What it means that it's not targeting Jupiter. Jupiter would kill it. Whatever. Atlas is, whatever materials it's made of, whatever systems it contains, a direct approach to Jupiter would be catastrophic. Let me explain why gas giants are absolutely lethal to anything fragile, and why choosing a moon instead of the planet reveals something crucial about Atlas's nature and purpose. Jupiter is not a gentle place. It's the solar system's gravitational monster, a failed star with 318 times Earth's mass, spinning so fast that its day is less than 10 hours long. That rapid rotation powers the most intense magnetic field of any planet, creating a magnetosphere so vast that if you could see it from Earth, it would appear larger than the full moon despite being over 600 million kilometers away. Within that magnetosphere, charged particles spiral along magnetic field lines, creating radiation belts that make Earth's Van Allen belts look harmless by comparison. Approaching Jupiter directly means flying through that radiation storm, absorbing doses that would fry electronics, degrade materials, and make any biological tissue non-viable within hours. But radiation is just the beginning. Jupiter's atmosphere is a roiling chaos of hydrogen and helium mixed with ammonia, methane, and other compounds, all churning in the storms larger than Earth, driven by internal heat from the planet's slow gravitational contraction. The Great Red Spot, that iconic oval storm, has been raging for at least 200 years, possibly 400. Wind speeds in the upper atmosphere exceed 400 kilometers per hour. Lightning bolts more powerful than anything on Earth flash constantly. And that's just the weather. If you tried to aerobrake into Jupiter, to use atmospheric friction to shed velocity, you'd be torn apart. The atmospheric density increases exponentially as you descend. The pressure climbs to crushing levels. The temperature soars. Even if your craft could somehow survive the descent, there's no coming back up. Jupiter's escape velocity is 59.5 kilometers per second. Nothing launched from within the atmosphere could achieve that without enormous fuel reserves, and fuel is weight, and weight makes the descent problem worse. It's a trap. A beautiful, scientifically fascinating trap, but a trap nonetheless. Contrast that with Callisto. Callisto offers a stable platform, low radiation, solid surface, minimal escape velocity, resources. From Callisto you have autonomy. You can operate for years, decades potentially, without the constant existential threat that proximity to Jupiter imposes. You can gather materials, perform repairs, launch missions deeper into the system or back toward the inner planets. A gas giant gives you nothing but danger. A moon gives you everything. This is exactly the logic human mission planners have used for decades. When NASA and ESA design missions to the Jovian system, they don't plan to send astronauts into Jupiter's atmosphere. They plan to establish bases on moons, specifically Callisto because it's the only location that balances safety with utility. The conclusion is inescapable. If Atlas is targeting Callisto instead of Jupiter, it's making the same strategic calculations that human engineers make. It's choosing the location that optimizes survival and capability. Let me give you a metaphor. Imagine you're a military planner approaching a hostile or unknown continent. You don't try to land on the mainland immediately. You secure an island offshore first. Islands give you a defensive position, a supply depot, a staging ground. You can observe from there. You can launch operations. You can retreat if necessary. Throughout human history, islands have been strategically critical precisely because they offer position without overcommitment. Callisto is Jupiter's island, the offshore platform from which you control access to the entire Jovian system. If Atlas's behavior is intentional, if there's navigation and purpose behind the trajectory, then the choice to avoid Jupiter and target Callisto suggests sophistication. It suggests understanding of orbital mechanics, of radiation environments, of resource availability. It suggests that whatever Atlas is, it's not mindlessly falling through the solar system. It's selecting terrain. It's establishing position. And that raises the darkest speculation of all. Is it avoiding detection, or is it claiming territory? There's a psychological dimension to this that's worth acknowledging. Human beings are pattern recognition machines. We see faces and clouds, conspiracies and coincidences, and intent where there's only randomness. It's a survival trait gone hyperactive. So when we observe an object behaving in ways that match what we would do in the same situation, when it targets the exact location we've identified as optimal, our brains scream intent. But patterns can be coincidental. Anomalies can be natural. The universe is strange enough without invoking aliens. And yet, the data keeps piling up. The trajectory keeps deviating. The models keep failing. At what point does skepticism become denial? Consider this. If Atlas achieves orbit around Callisto, if it maintains position there, what can we do about it? The answer is very little. We have no spacecraft currently in the Jovian system. Juno is studying Jupiter, but it's in a polar orbit around the planet itself, not positioned to intercept or closely observe an object near Callisto. We could launch a mission, but the travel time to Jupiter is years. By the time we arrived, Atlas could have been stationed there for half a decade or more. We'd be arriving after the fact, studying something that's already established, already operating, already accomplishing whatever it came to accomplish. The speed of light is fast, but the speed of spacecraft is agonizingly slow. We're outpaced, we're behind, we're reactive, not proactive. And here's the final unsettling piece. Callisto is where we were going. Human mission. Architectures for the 2030s and 2040s include Callisto bases. It's in the plans. It's been studied, modelled, proposed, and advocated for by space agencies around the world. If something else arrives there first, if something claims that position before we can, what does that mean for humanity's expansion into the solar system? Do we share? Do we negotiate? Do we avoid? Or do we find ourselves in the bizarre position of needing to approach an unknown object of unknown origin and unknown purpose and ask permission to use the moon we've been planning to colonize for decades? These questions don't have comfortable answers. They have uncertain answers, speculative answers, and answers that depend entirely on what Atlas turns out to be. Natural object with exotic physics, uncomfortable but ultimately scientific. Controlled object with intent, that changes everything. It changes our understanding of our place in the galaxy. It changes the assumptions underlying every space policy and exploration plan. It changes the future. But we're not done yet. Because while Atlas is approaching Callisto, while trajectory analysts are quietly arguing over models in private forums, while agencies maintain their careful silence, the astronomical community is having a completely different conversation. A conversation about data sharing, about institutional caution, about the divide between what official sources will say and what independent researchers are willing to speculate. That conversation reveals another layer to this mystery, one that's less about physics and more about how we decide what's real when the evidence is uncomfortable and the implications are vast. Part 6. The Quiet Observatory Division. The split between public and private models. There are two versions of Atlas's story being told right now, and most people only know about one of them. The official version, the one you'll find in NASA's Jet Propulsion Laboratory databases and European Space Agency bulletins, describes 3I Atlas as an interstellar comet exhibiting unusual but not unprecedented non-gravitational forces. The language is careful, technical, hedged with uncertainties. Trajectory solutions are updated periodically as new observations refine the orbital elements. Everything is presented with the measured caution that institutional science demands. But there's another version, circulating in private astronomy communities, shared across Discord servers and Slack channels, discussed in late-night emails between researchers who've known each other for years. That version is far more alarming. The split between public and private models isn't new to astronomy. Professional researchers have always had informal networks where they share preliminary findings, debate controversial interpretations, and test ideas that aren't ready for peer review. What's different about Atlas is the degree of divergence between what institutions are willing to say publicly and what independent analysts are concluding privately. The gap is wider than usual, and it's growing. Here's how it works. When you track an object through space, you're solving a complex gravitational puzzle. You account for the sun's gravity, the gravity of planets, radiation pressure from sunlight, and any non-gravitational forces like outgassing. You fit the observations to a mathematical model, adjusting parameters until the predicted positions match the observed positions within acceptable error margins. It's an iterative process, computationally intensive, and it requires making assumptions about what forces are acting on the object. Official institutions, NASA, ESA, the Minor Planet Center, use conservative assumptions. They stick with known physics, established mechanisms, forces we understand well. This is good scientific practice. You don't invoke exotic explanations when conventional ones might suffice. But independent researchers aren't bound by institutional caution. They can run more daring orbital fits, experiment with unusual parameter sets, test models that assume forces we don't fully understand. Over the past several months, small research groups around the world have been doing exactly that with Atlas's data. They've taken the same observations that NASA uses, the same positional measurements and brightness data, and they fit them to models that allow for directed thrust, for propulsive maneuvers, for controlled braking. And those models fit the data better, significantly better. One particular model, circulating in a private astronomy forum frequented by about 30 professional and amateur researchers, incorporates what its creator calls the Callisto capture corridor. This isn't wild speculation. It's rigorous orbital mechanics. The researcher, who has a background in trajectory optimization for spacecraft missions, calculated the precise velocity changes required for an object approaching from interstellar space to enter stable orbit around Callisto. The requirements are stringent. You need to brake at specific times along specific vectors. You need to shed velocity gradually enough that you don't destabilize your trajectory, but quickly enough to complete the maneuver before geometry stops cooperating. The window is narrow. When this researcher applied those requirements to Atlas's observed trajectory, the fit was unsettling. The object's velocity profile matches the predicted braking pattern for the first phase of Callisto capture. Not perfectly, orbital mechanics never yield perfect matches in the real world, but well enough that dismissing it as coincidence requires effort. The negative delta-V events, those tiny braking pulses that official models attribute to asymmetric outgassing, line up with when and where you'd expect to see course corrections if the goal were orbital insertion around Callisto. The timing works, the vectors work, the energetics work, but you won't find this model in any official database. You won't see it cited in press releases or mentioned in NASA updates. Why? Because institutions are conservative by necessity and design. They avoid speculative interpretations that could be wrong and embarrassing. They wait for overwhelming evidence before making extraordinary claims. This is generally wise. Science has been burned before by jumping to exotic conclusions prematurely. Cold fusion, faster-than-light neutrinos, arsenic-based life in Mono Lake. Each time, the extraordinary claim collapsed under scrutiny, leaving researchers red-faced and the public more skeptical of scientific pronouncements. So institutions err on the side of caution. They publish what they can defend rigorously, and keep the wilder speculations private. The political angle matters too. Governments dislike publicly admitting that unexplained phenomena are occurring, especially phenomena in space that could have implications for national security or international relations. If an object is demonstrating controlled navigation through the solar system, that's not just a scientific curiosity, it's a potential threat, or at minimum, an intelligence concern requiring coordinated governmental response. Public statements would trigger questions that nobody has good answers for yet. What is it? Where did it come from? What does it want? Can we communicate with it? Should we? Those conversations need to happen internally first, among people with security clearances and diplomatic experience, before they happen in press conferences and congressional hearings. So the official channels remain quiet while independent researchers grow increasingly convinced that something extraordinary is occurring. The divide creates tension. Some independent analysts feel frustrated that institutions aren't acknowledging what the data clearly suggests. Some institutional scientists feel that independent analysts are overinterpreting noisy data and promoting sensationalism. Both sides have valid points. The data is genuinely anomalous, but anomalies have natural explanations more often than not. Yet the longer the trajectory deviations continue, the harder it becomes to construct plausible natural scenarios that explain everything. We've seen this pattern before, when the star Keck 8462852, better known as Tabby's star, began exhibiting bizarre dimming patterns in 2015, the astronomy community split similarly. Official papers cautiously discussed dust clouds and cometary fragments. But in private communications and public forums, researchers debated megastructures, alien artifacts, Dyson swarms. The speculation ran wild until further observations suggested a prosaic explanation involving circumstellar dust. The lesson seemed clear. Exotic explanations are almost always wrong, but almost always isn't always. And Oumuamua, that earlier interstellar visitor, still lacks a fully satisfactory natural explanation for its acceleration. Some astronomers remain convinced it was just an unusual comet. Others think we're missing something fundamental about interstellar objects' composition or behaviour. The debate never fully resolved. Atlas feels different, though. Oumuamua accelerated, which at least has comet analogues. Atlas is braking, which has no good natural parallel. Oumuamua's trajectory was well determined but unremarkable in its geometry. Atlas's trajectory is converging on an orbital capture corridor that requires specific velocity profiles. The strangeness compounds. And because the strangeness compounds, the private conversations among researchers have grown more urgent. Data sets are being shared more freely. Collaborations are forming outside official institutional structures. People who normally guard their data jealously are opening up because they want independent verification of what they're seeing. When scientists start acting like that, when competition gives way to concerned cooperation, it suggests they're genuinely worried about what they're observing. Here's a question that keeps appearing in those private discussions. Are government observatories withholding high-resolution spectroscopy? Spectroscopy reveals an object's composition by analysing the wavelengths of light it reflects or emits. With Atlas, early spectroscopic observations suggested a cometary composition, water ice and volatiles, but those observations were low-resolution snapshots taken when the object was still far from the Sun. Higher resolution spectroscopy performed closer to perihelion would reveal much more: precise chemical abundances, isotopic ratios, molecular signatures. That data would help determine whether Atlas is truly a comet or something masquerading as one. but detailed spectroscopic results haven't been published. Some researchers suspect the data exists but remains classified or unpublished for reasons nobody will state openly. Others think it simply hasn't been obtained because telescope time is limited and Atlas wasn't considered high priority enough. Both explanations are plausible. Both are unsatisfying. The tension between public caution and private alarm is reaching a tipping point. At some point, if Atlas continues behaving anomalously, if it achieves Callisto orbit, someone will go public with the full scope of the alternative models. A paper will be submitted to a journal, or a researcher will give a conference talk that gets picked up by science journalists, or someone will simply post a detailed analysis on a public forum. When that happens, the conversation will explode. The careful institutional language will be drowned out by speculation and debate. And the question everyone will ask is, how long have you known about this? Why didn't you tell us sooner? But before we get lost in the conspiracy theories and the institutional politics, we need to step back and ask a bigger question. Has this happened before? Not just in our solar system, where we've only been watching carefully for a few decades, but out there in the broader galaxy. Are there patterns we're missing? Is Atlas unique? Or is it part of something larger, something that's been happening quietly throughout the Milky Way, while we've been too young and too isolated to notice? Part 7, has another civilization done this before? The galactic patterns theory. The Milky Way is approximately 100,000 light-years across, and contains somewhere between 100 billion and 400 billion stars. Most of those stars have planets. Many of those planets orbit in habitable zones, where liquid water could exist. Some fraction, nobody knows what fraction, might develop life. Some smaller fraction might develop intelligence. Some even smaller fraction might develop technology capable of interstellar travel. When you multiply all those fractions together, even conservative estimates suggest that if we're not alone, we're definitely not the first. Which raises an interesting question. If other civilizations have existed for millions or billions of years, developing technologies far beyond ours, would they have left traces? Would there be patterns in the galaxy that we could detect if we knew what to look for? There's a small, somewhat fringe subfield of astronomy that studies exactly this question. It's called astroarchaeology, and it searches for signs of ancient or ongoing extraterrestrial activity by looking for anomalies in large data sets. Unusual stellar motion, objects with trajectories that don't fit natural models, concentrations of debris in improbable locations. Most of the time, these searches find nothing, or they find things that initially look interesting but turn out to be mundane upon further investigation. But occasionally, very occasionally, something genuinely weird shows up in the data, and nobody quite knows what to make of it. One of the most intriguing concepts in this field is the idea of gravitational waypoints. Stars and planets don't just sit still in space. They orbit the galactic center in vast, slow circuits that take millions of years to complete. As they move, they create temporary gravitational configurations, windows where a traveling object could use sequential gravity, assist to redirect itself with minimal energy expenditure. If you're crossing the galaxy, and you want to conserve fuel or reaction mass, you'd plan your route to take advantage of these waypoints. You'd hop from star to star, using each one's gravity to adjust your trajectory, threading a path through the galaxy that minimizes the energy cost of course corrections. It's the interstellar equivalent of sailing, using natural forces to go where you want to go rather than fighting against them constantly. Moons, particularly large moons around gas giants, would be ideal stopping points along such routes. They offer stable orbits, radiation shielding if positioned correctly, and potential resources. Of all, civilizations sending probes or vessels across the galaxy might target these moons specifically, establishing temporary or permanent stations where objects could rest, refuel, or wait for the next favourable gravitational window. This is pure speculation, of course, but it's physically plausible speculation. The physics allows it. The strategic logic supports it. The question is whether anyone has actually done it. Some researchers have tried looking for evidence in asteroid catalogues and rogue object databases. These catalogues contain millions of entries, most of them unremarkable rocks following predictable orbits. But buried in those millions of entries are statistical outliers, objects whose velocities or trajectories don't fit the expected distributions. Most outliers are probably just measurement errors or rare natural phenomena. But if even a tiny fraction represents something else, something with a different origin, you'd expect to see subtle patterns. clusters of anomalies near gravitationally significant locations, trajectories that converge on moons more often than random chance would predict, velocity distributions with unexplained tails. So far, no definitive patterns have been identified. The data is too noisy, the sample size is too small, the uncertainty is too large. You can find correlations if you look hard enough, but correlations aren't causation, and most apparent patterns dissolve under rigorous statistical testing. Still, the search continues because the implications of finding a pattern would be profound. If we could demonstrate that interstellar objects preferentially target certain types of moons or show velocity profiles inconsistent with natural motion, it would suggest that someone somewhere has been navigating through the galaxy for a very long time. It would mean we're not alone, and possibly that we're very late to a game that's been ongoing for eons. Atlas's velocity profile is interesting in this context because it looks like something that's been slowing down gradually over an enormous distance. Interstellar objects typically maintain their velocities across the vast emptiness between stars. There's nothing out there to slow them down. Space is a vacuum. Drag is negligible. Yet Atlas's current velocity, even accounting for solar gravitational acceleration and deceleration, seems lower than you'd expect for an object arriving from the galactic neighbourhood. Some researchers, speculating wildly, have suggested that Atlas might have been braking, not just since entering the solar system, but for years or decades before that, gradually reducing its speed across light years of space to match the local stellar motion and arrive at Jupiter with a velocity profile suitable for capture. This is extremely speculative and requires mechanisms we don't understand. What could produce thrust across interstellar distances? Solar sails work near stars but are useless in deep space. Fusion drives are theoretically possible but would require enormous fuel reserves. Antimatter propulsion, if possible, might allow such maneuvers but is far beyond our current capabilities. Or maybe there's physics we haven't discovered yet. Exotic propulsion methods that use quantum vacuum fluctuations, or space-time manipulation, or other concepts that sound like fantasy, but might be standard technology for sufficiently advanced civilizations. We simply don't know. Our ignorance is vast. Let me offer a thought experiment. Imagine a civilization that developed interstellar travel 10 million years ago. They sent probes throughout the galaxy, small autonomous objects programmed to hop from star to star, using moons as waypoints, gathering data, possibly even establishing small relay stations or resource caches. Over millions of years, these probes would spread across thousands of star systems, creating a network, a galactic infrastructure invisible to anyone who didn't know what to look for. Now fast forward to the present day. Most of those probes would have failed by now, degraded by radiation, or collisions, or simple mechanical failure. But a few might still be operational, still following their programming, still moving from waypoint to waypoint. Would we recognize such an object if it entered our solar system? Would it look like Atlas? I'm not saying that's what Atlas is. I'm saying that when you contemplate the age of the galaxy and the possibility of civilizations far older than ours, you have to admit that the universe could contain things we're not prepared to understand. Our technology is barely a century old. Radio telescopes, space probes, orbital mechanics, these are all incredibly recent inventions. Civilizations with millions of years head start on us might have technologies that appear indistinguishable from magic or nature. We might be surrounded by artifacts and never recognize them as such because they don't fit our narrow expectations of what artificial objects should look like. The counter-arguments are strong, and they deserve acknowledgement. First, we've never found verified evidence of extraterrestrial artifacts despite decades of searching. The simplest explanation for that is we're alone, or at least very isolated. Second, interstellar travel is monumentally difficult even for advanced civilizations. The distances are crushing, the energy requirements staggering, the timescales inhuman. Maybe it's just not worth doing. Maybe civilizations stay home. Third, measurement errors and natural anomalies are common. Extraordinary claims require extraordinary evidence, and Atlas's trajectory, while strange, isn't yet strange enough to overcome the burden of proof required for claims of artificial origin. These counter-arguments are valid and important. Science progresses by skepticism, by demanding rigorous proof before accepting revolutionary ideas. But skepticism isn't the same as closed-mindedness. When the data persistently refuses to fit natural models when multiple independent, Analyses reach similar unsettling conclusions. Intellectual honesty demands considering uncomfortable possibilities, not accepting them prematurely, but considering them seriously. That's where we are with Atlas. We're in the uncomfortable space between probably natural and possibly not, and the longer the object continues behaving anomalously, the harder it becomes to stay comfortably on the natural side of that divide. So maybe other civilizations have done this before. Maybe moons throughout the galaxy serve as waypoints for travellers we'll never meet, or meet only when they choose to reveal themselves. Maybe Atlas is part of a network older than human civilization, and we're only now stumbling across it because we've finally developed the technology to notice. Or maybe, and this is equally possible, Atlas is just a weird comet doing weird comet things, and we're pattern matching ourselves into fantasy. The honest answer is we don't know yet. But we're about to find out because Atlas is getting closer to Callisto every day, and eventually ambiguity will give way to clarity. What that clarity reveals could rewrite our understanding of our place in the cosmos. But before we get there, we need to address another mystery, one that's arguably more immediate and more troubling. What does Atlas actually look like, and why can't anyone seem to agree? Part 8. The structural anomalies. Nobody agrees on. If you ask 10 different astronomers to describe Atlas's physical structure, you'll get 10 different answers. That shouldn't happen. We have powerful telescopes. We have radar systems capable of imaging near-Earth objects with meter-scale resolution. We have spectroscopy that can determine chemical composition. Yet Atlas remains frustratingly ambiguous, a blur of contradictory observations that refuse to coalesce into a coherent picture. Some of this is understandable. The object is far away, currently well beyond Mars as it approaches Jupiter, and distant objects are hard to characterize precisely. But some of the contradictions go deeper than distance alone can explain. Radar observations are the source of some of the most disputed claims. Radar astronomy works by bouncing radio waves off an object and analyzing the return signal. The time delay tells you distance. The frequency shift tells you velocity. The shape and strength of the return signal tell you about the object's size, rotation, and surface properties. Several observatories attempted radar observations of Atlas during its approach to perihelion. The results were confusing. One facility reported a return signal consistent with a roughly spherical object, maybe 5 to 7 kilometers across, tumbling chaotically. But another facility, using a different frequency and observation geometry, reported echoes suggesting a distinctly non-spherical shape, something elongated or possibly even segmented, like multiple components loosely bound together. These discrepancies could be equipment differences. Radar astronomy is technically challenging. You're detecting incredibly faint echoes from millions of kilometers away. Signal-to-noise ratios are terrible. Processing pipelines differ between observatories. Calibration errors can produce artifacts that look like real features. So maybe the contradictory radar results just reflect the difficulty of the observations rather than genuine structural weirdness. But there's another possibility. Maybe Atlas's structure is genuinely ambiguous, something that doesn't fit our categories. We're used to astronomical objects being either solid bodies like asteroids or diffuse clouds like comets with their comae. Atlas might be something in between, or something altogether different. The coma behavior adds another layer of mystery. A coma is the cloud of gas and dust that surrounds an active comet when solar heating sublimates surface ices. Atlas definitely has a coma. Images show a fuzzy envelope surrounding the central nucleus. But the coma's density distribution is strange. Most comets have symmetric or slightly asymmetric coma, with denser material on the sunward side where sublimation is strongest. Atlas's coma shows irregular density variations that don't correlate cleanly with solar heating. One research group analysing photometric data claimed to detect a hollow core, a region near the nucleus where the coma density drops unexpectedly. Another group looking at the same data saw instead a ring-shaped emission pattern, like the coma was being ejected from a specific equatorial band rather than uniformly from the surface. These competing interpretations might both be wrong. Coma modelling is complex. You're trying to reconstruct a three-dimensional gas cloud from two-dimensional images, and the mathematics involves assumptions about particle velocities, sublimation rates, and dust-to-gas ratios. Different assumptions yield different models. but the fact that serious researchers are arriving at wildly different structural conclusions suggests the underlying data is genuinely anomalous. Normal comets don't produce this much interpretive ambiguity. Their coma behaviour fits standard models reasonably well. Atlas doesn't, and that bothers people. Then there are the rotation anomalies. Most small bodies in the solar system rotate predictably. Their light curves, the way their brightness varies over time, show regular periodic patterns corresponding to the rotation period. If a body is elongated, it appears brighter when you see its long axis, and dimmer when you see its short axis, producing a sinusoidal light curve with a period equal to the rotation time. Atlas's light curve is erratic. There's no clear periodicity. Some observers report detecting rotation periods of several hours, but those periods don't hold. The brightness variations change over time in ways that suggest either complex tumbling with multiple rotation axes or surface features that activate and deactivate independently. Neither explanation is fully satisfying. Exotic hypotheses have emerged to explain these structural oddities. Some researchers have suggested that Atlas might be tumbling chaotically due to asymmetric outgassing, where jets firing from different locations produce torques that change the rotation state unpredictably. That's possible. We've seen it with other comets, but it usually produces light curves with recognizable components, even if they're complex. Atlas's light curve looks more random than complex. Another hypothesis involves rotating panels or surfaces. If Atlas had distinct sections with different reflectivities or emission properties, and those sections moved relative to each other, you'd see irregular brightness variations. But why would a natural object have such a configuration? There's no obvious formation mechanism that would produce it. A few fringe voices, mostly in internet forums rather than peer-reviewed journals, have suggested structured geometry. They point to the radar echoes and the coma anomalies and argue that Atlas might not be a natural body at all, but something constructed, something with internal compartments or framework. This is where the conversation usually derails, because claiming artificial origin without definitive proof is scientific suicide. Careers have been destroyed by less, so mainstream researchers avoid saying it directly, even if some privately wonder. They use careful language. They talk about unusual surface properties or unexpected compositional heterogeneity. They publish papers analysing the anomalies without drawing conclusions about what those anomalies mean. The gap between what people observe and what they're willing to state publicly is growing. There's one more structural anomaly worth mentioning, though it's contested and poorly documented. Several independent observers claim to have detected thermal emissions from Atlas that don't match solar heating models. All objects in space absorb sunlight and re-radiate that energy as infrared radiation. The amount and distribution of infrared emission depends on the object's size, reflectivity, rotation, and thermal properties. For most comets and asteroids, you can predict the infrared signature reasonably well. Atlas's infrared emissions, according to these claims, are higher than expected, particularly on the night side where solar heating should be minimal. This could indicate internal heat sources. Radioactive decay can produce internal heating, but you'd need a lot of radioactive material to generate detectable emissions from kilometers away. Tidal heating, like what keeps Jupiter's moon, eovolcanic, doesn't apply because Atlas isn't in a tight orbit around anything. So where's the heat coming from? The most generous interpretation of all these structural anomalies is that Atlas is a comet with unusual composition and morphology, perhaps an interstellar visitor formed in conditions very different from the solar nebula that birthed our solar system's comets. Different chemistry, different thermal history, different ice-to-rock ratios, all of that could produce unusual behaviour that doesn't fit our Earth-informed models. This is the conservative, scientifically respectable interpretation. It might even be correct. But it requires accepting a remarkable string of coincidences, an unusual structure, unusual coma behaviour, unusual thermal emissions, and unusual trajectory all occurring in the same object. At what point do multiple unusual features compound into something beyond unusual and into something unexplainable by natural processes alone? Comparing Atlas to Oumuamua is instructive. Oumuamua sparked a similar debate about structure. Initial observations suggested an elongated shape, maybe 10 times longer than wide, spinning rapidly. That was strange, but not impossible. Later analyses suggested maybe it was pancake-shaped instead, flat and round. The shape debate never fully resolved, but everyone agreed Oumuamua was solid, a single coherent object, not a loose collection of fragments or something with internal structure. Atlas doesn't have even that level of consensus. We can't agree on whether it's spherical or elongated, solid or segmented, inert or thermally active. The ambiguity persists despite months of observations from multiple facilities. That shouldn't happen with modern instruments and techniques, unless the object is deliberately ambiguous, deliberately resisting easy categorization, unless its structure is unlike anything we've encountered before. I'm not going to tell you what Atlas looks like because nobody knows. The data won't cooperate. The observations contradict. The models fail. And that uncertainty, that fundamental inability to pin down basic physical properties, despite our best efforts, feeds every conspiracy theory and exotic hypothesis circulating in the darker corners of the internet. Because if we can't figure out what it looks like, how can we possibly figure out what it is or what it wants? Those questions bring us to the conspiracy layer, the realm where speculation becomes storytelling and where people start believing that Atlas didn't arrive at Callisto by accident. They believe it was the goal all along. Part 9. The conspiracy layer. Why some believe Callisto was the goal all along. Let's be clear about something from the start. What I'm about to describe is not established fact. It's speculation built on anomalies, pattern matching built on coincidence, a narrative built on the human need to find meaning in mysterious events. But it's worth examining because it reveals how people think about Atlas when freed from institutional caution and scientific restraint. And sometimes, just sometimes, conspiracy theories stumble onto truths that more respectable venues refuse to acknowledge. So let's explore the idea that Callisto wasn't a target of opportunity. It was the destination all along. The conspiracy version of events starts with a simple premise. If Atlas is artificial, if it's a probe or vessel from another civilization, then its journey to our solar system was planned. You don't travel between stars accidentally. The energies involved, the timescales, the precision required for navigation, all of it implies intent and forethought. So if Atlas entered the solar system deliberately, it entered with a destination in mind. That destination, according to this theory, was always Callisto. Why Callisto specifically? Because of its unique combination of safety and strategic value. We've already established that Callisto sits outside Jupiter's lethal radiation belts, making it the only large Jovian moon where long-term survival is plausible. But conspiracy theorists take this further. They argue that any civilization capable of interstellar travel would have surveyed our solar system remotely, perhaps decades or centuries before sending anything physical. They would have mapped gravitational fields, identified resource deposits, and analyzed radiation environments. When they decided to establish a presence here, they would have chosen the optimal location. And for the outer solar system, that location is unambiguously Callisto. Compare Callisto to Europa, the moon everyone's excited about because of its subsurface ocean and potential for life. Europa orbits deep within Jupiter's magnetosphere, absorbing radiation doses that would destroy electronics and degrade materials within months. Any installation on Europa would need meters of shielding, massive power systems to maintain, and constant maintenance to repair radiation damage. It's a terrible forward operating base despite its scientific interest. Io, the innermost large moon, is even worse. It's the most volcanically active body in the solar system, convulsing with tidal forces that generate continuous geological chaos. Sulfur eruptions, lava flows, and apocalyptic radiation make Io essentially uninhabitable for anything we can imagine. Ganymede, the largest moon in the solar system, has its own magnetic field that offers some protection, but it's still closer to Jupiter than Callisto and receives significantly higher radiation. Only Callisto offers the calm environment necessary for something to park long-term without constantly fighting environmental hazards. The resource argument goes beyond just water. Callisto is geologically dead, meaning stable. There are no tectonic shifts, no volcanic surprises, no geological processes that could endanger structures or installations. The surface hasn't changed significantly in billions of years. If you build something there, it stays built. For long-duration operations, for installations meant to last decades, centuries, or longer, geological stability is crucial. You don't want to establish a base on a moon that might shift underneath you. Callisto is as stable as it gets. Then there's the surveillance angle, and this is where conspiracy theories venture into darker territory. Callisto's orbit offers a vantage point over the entire inner solar system. With minimal instrumentation, something stationed at Callisto could observe Earth, Mars, the asteroid belt, essentially anywhere humans currently operate or plan to operate. The line of sight is clear. The distance is far enough to avoid detection, but close enough for effective observation with advanced sensors. If your goal is to monitor a developing civilization without revealing yourself, Callisto is an ideal observation post. You're hidden in plain sight, disguised as an unremarkable moon in a system full of moons, watching and waiting. Mythological symbolism adds a narrative layer that conspiracy theorists love. Callisto, in Greek mythology, was a nymph transformed into a bear and eventually placed among the stars as the constellation Ursa Major. The name means most beautiful, but the mythological Callisto was also a victim, hunted and transformed, forever separated from her original form. Some see parallels in the moon itself, a world separated from the dangerous chaos of Jupiter, transformed into a safe harbour. Others point out that Callisto represents sanctuary, a place of refuge where the hunted can hide. These mythological connections don't mean anything scientifically, but they resonate emotionally, adding a storytelling depth to the conspiracy narrative. The forums where these theories circulate, Reddit's astronomy and UFO communities, specialized Discord servers, fringe science websites, they analyze Atlas's trajectory with obsessive detail. They plot velocity vectors, calculate energy budgets, and compare the maneuvers to spacecraft trajectories designed by human mission planners, and they find unsettling similarities. The braking profile Atlas is following resembles optimal control solutions for orbital insertion. The timing of the velocity changes matches when course corrections would be most efficient, given Jupiter's gravitational field and Callisto's orbital position. If you were designing a mission to capture into Callisto orbit using minimal fuel, you'd execute maneuvers very similar to what Atlas appears to be doing. That's either remarkable coincidence or something more. Counter-arguments exist, and they're strong. First, all of this assumes Atlas is artificial, which remains unproven. Natural objects can exhibit complex behaviors that superficially resemble control without any actual intelligence behind them. Second, selection bias is real. If you're looking for patterns, you'll find them whether they're meaningful or not. Human brains are exceptional pattern recognition engines, but they're also prone to false positives, seeing faces in clouds and conspiracies in coincidence. Third, the physics of Atlas's trajectory can still be explained by exotic but natural phenomena. We don't understand everything about interstellar objects. Maybe Atlas is behaving exactly how interstellar comets behave, and we're just not familiar enough with them yet to recognize normal behavior when we see it. These counter-arguments deserve respect. Jumping to artificial explanations prematurely is bad science and bad thinking. Extraordinary claims require extraordinary evidence, and Atlas's behavior, while anomalous, hasn't crossed that threshold for most serious researchers. But the conspiracy theories persist and grow because the anomalies keep accumulating. Each new observation that defies simple explanation adds fuel to the speculation. Each trajectory update that brings Atlas closer to the predicted capture corridor reinforces the narrative. And the institutional silence, the lack of detailed public explanations for why Atlas is behaving this way, creates a vacuum that conspiracy theories rush to fill. Here's the uncomfortable truth. If Atlas does achieve stable orbit around Callisto, if it parks there and remains there, the conspiracy theories become much harder to dismiss. Natural capture is so improbable that observing it would demand rethinking, either our understanding of orbital mechanics or our assumptions about Atlas's nature. At that point, the exotic explanations become less exotic and more necessary. At that point, the question shifts from "is it artificial?" to "what do we do about it?" Science fiction writers have been imagining megastructures and alien installations on moons for decades. Callisto appears frequently in these stories precisely because its properties make it the logical choice for anyone seeking to establish a base in the Jovian system. Arthur C. Clarke set part of his Space Odyssey series on Callisto. Countless others have used it as a staging ground for outer solar system exploration. The moon has become synonymous in speculative fiction with strategic positioning and forward operations. So when something from interstellar space appears to target Callisto specifically, when its trajectory matches what science fiction has been predicting for years, the boundary between fiction and reality blurs uncomfortably. Are we watching life imitate art? Or have storytellers been intuitively grasping a strategic logic that applies universally, regardless of whether you're human or something else entirely. The conspiracy layer of Atlas's story matters not because it's necessarily true, but because it reveals our anxieties and assumptions. We're a young civilization, barely beginning to explore our own solar system, suddenly confronted with something that doesn't fit our expectations. We don't know if it's natural or artificial. We don't know its purpose or origin. We don't know if it's aware of us or indifferent. That uncertainty terrifies us because it strips away the comforting illusion that we understand our cosmic neighborhood. So we construct narratives, we build theories, we try to impose meaning on mystery because humans need stories to make sense of chaos. Whether those stories are correct is almost secondary. What matters is that we're forced to tell them, forced to confront possibilities that seemed safely confined to fiction until Atlas arrived. But let's zoom out now, pull back from the conspiracy theories and the structural mysteries and the trajectory debates, and look at what Callisto represents in the broader context of human ambition and cosmic geography. Because regardless of whether Atlas is natural or artificial, its apparent targeting of Callisto raises a fundamental question about the future. What does control of that moon mean for whoever holds it? And what happens if humanity finds itself in competition for the most valuable real estate in the outer solar system? Part 10. The broader cosmic chessboard. What Callisto represents in the long game. Space agencies don't talk about it publicly, but privately. Among mission planners and long-term strategists, there's a consensus that's been building for decades. Callisto is the key. Not Mars, despite all the public enthusiasm for the red planet. Not the Moon, despite its proximity and romantic appeal. Not even Europa, with its tantalizing subsurface ocean. Callisto is the linchpin of humanity's expansion into the outer solar system, the single most strategically valuable location beyond the asteroid belt. And if you understand why, you understand why Atlas's apparent trajectory toward that moon should alarm anyone thinking seriously about humanity's cosmic future. Let me explain the logic. Mars is important for symbolic and scientific reasons. It's the closest potentially habitable planet, and establishing a self-sustaining Mars colony would be a monumental achievement for our species. But Mars doesn't give you the outer solar system. It's still deep in the sun's gravity well, still expensive to launch from, still limited in its strategic reach. The moon is valuable as a testing ground and possibly as a manufacturing hub using lunar regolith, but it doesn't position you for deep space exploration. It keeps you tied to Earth-Moon space, forever circling our home planet. Europa might harbour life, which would be the greatest scientific discovery in human history, but it's a research destination, not a base. The radiation environment prohibits long-term habitation without enormous infrastructure investments that might never be economically viable. Callisto, though. Callisto changes the game entirely. NASA's early plans for human exploration of the Jovian system, going back to studies in the late 1990s and early 2000s, consistently identified Callisto as the optimal location for a permanent base. The reasoning is straightforward once you understand the physics. Callisto sits far enough from Jupiter to be safe, but close enough to serve as a hub for operations throughout the Jovian system. From Callisto, you can launch missions to Europa for scientific research. You can study Jupiter's atmosphere and magnetosphere. You can mine water ice for propellant. You can use Jupiter's immense gravity for slingshot maneuvers that send spacecraft towards Saturn, Uranus, Neptune, and beyond with minimal fuel expenditure. The European Space Agency reached similar conclusions independently. Their Jupiter Icy Moons Explorer mission, JUICE, which launched in 2023, includes detailed observations of Callisto specifically to assess its suitability as a future base site. The mission will map water ice deposits, characterize the surface composition, measure the radiation environment, and identify potential landing sites. This isn't idle curiosity. This is reconnaissance. Space agencies are preparing for an era when human presence in the outer solar system becomes possible, and they're doing the groundwork now to understand where that presence should be established. Think of Callisto as the equivalent of strategic island bases on Earth. Diego Garcia in the Indian Ocean, Guam in the Pacific, Hawaii as a mid-Pacific waypoint. These locations aren't valuable because they're particularly pleasant or resource-rich on their own. They're valuable because of their position. They project power. They enable operations across vast regions that would be impossible without forward bases. They're nodes in a network, anchors for influence and capability. Callisto serves the exact same function in the outer solar system. It's not the destination, it's the platform that makes every other destination accessible. The economic logic is equally compelling. Water is the currency of space exploration. Rocket fuel is expensive primarily because lifting it out of Earth's gravity will cost enormous amounts of energy and money. But if you can manufacture fuel in space using local resources, if you can crack water ice into hydrogen and oxygen, and fill your tanks at Callisto instead of launching from Earth with everything you need, the cost structure of deep space exploration transforms completely. Missions become cheaper. Risks decrease because you can carry less fuel initially, knowing you'll refuel at Callisto. Travel times to the outer planets shrink because you can afford higher energy trajectories. Callisto becomes a gas station, and whoever controls the gas station controls access to everything beyond. This isn't speculative futurism. Multiple private space companies and government agencies are actively working on ISRU technologies, in situ resource utilization, the ability to harvest and process materials in space. Moon-based and Mars-based ISRU experiments are already in development. Callisto is the logical extension of that technological pathway. If we can crack water ice on the Moon, we can do it on Callisto. And the strategic implications of establishing that capability first, of being the civilization that builds the refueling infrastructure in the outer solar system, are staggering. You become the gatekeeper. Other nations or entities wanting to explore beyond Jupiter have to either cooperate with you or invest enormous resources to establish competing infrastructure. First mover advantage in space is measured in decades and trillions of dollars. Now imagine that something else has arrived at Callisto first. Imagine Atlas achieves orbit, parks itself there, and establishes some kind of presence, whether that's active operation or dormant observation or something we can't yet categorize. What does that do to humanity's long-term plans? Do we proceed as if nothing has changed? Do we launch missions to Callisto knowing there's already something there? Do we attempt communication? Do we avoid the area entirely out of caution or fear? These aren't abstract philosophical questions. They're practical strategic dilemmas that space agencies and governments might face within the next decade. The symbolic dimension matters too. Callisto represents humanity's next frontier. For a species that's spent its entire existence confined to one planet, recently taking baby steps to the Moon and Mars, the idea of establishing permanent presence around Jupiter represents a threshold crossing. We'd be an interplanetary civilization in a meaningful sense, not just visiting other worlds but living and working throughout our solar system. That transition from single-planet species to multi-world civilization is arguably one of the most important evolutionary steps any species can take. It's the difference between being vulnerable to planetary-scale extinction events and being resilient enough to survive almost any catastrophe. It's the difference between remaining forever at home and becoming a spacefaring species capable of reaching other star systems eventually. So if something beat us to Callisto, if an interstellar visitor claimed that position before we could, it doesn't just disrupt our plans, it challenges our sense of agency and destiny. Throughout human history, exploration has been something we do to the universe. We discover, we map, we claim, we settle. The idea that we might arrive at a destination and find it already occupied, especially by something from beyond our solar system, inverts that relationship. Suddenly we're not the explorers, we're the latecomers, we're the species arriving to find the good real estate already taken. That psychological shift, from protagonist to secondary character in our own cosmic story, would be profound and unsettling in ways that transcend simple strategic concerns. There's a geopolitical angle that's impossible to ignore. Currently, space exploration is governed by the Outer Space Treaty of 1967, which declares that celestial bodies cannot be claimed by any nation. Space is the common heritage of humanity. But that treaty was written when space exploration was purely governmental and symbolic. As commercial space industries mature, as the economic value of space resources becomes tangible rather than theoretical, pressure to revise or ignore the Outer Space Treaty grows. If Callisto becomes genuinely valuable, if control of that moon translates to dominance of outer solar system exploration, nations will compete for access and influence. We've seen this pattern on Earth countless times. Resources attract competition. Competition breeds conflict. There's no reason to expect space will be different once the stakes become real. Now add an unknown variable to that equation. If Atlas establishes presence at Callisto, every nation's calculations change. Do you compete with other human nations for access, or do you cooperate to present a unified approach to the non-human entity that got there first? Does the existence of Atlas unite humanity or divide it? History suggests both outcomes are possible depending on leadership, circumstance, and the specifics of the situation. But one thing is certain: the arrival of something from interstellar space at the location we've identified as strategically critical would force conversations that have been safely theoretical until now. Questions about how to respond to extraterrestrial intelligence, about protocols for communication, about sharing space with non-human entities, would become urgent practical matters requiring immediate policy decisions. The long game, the cosmic chessboard, extends beyond just Callisto, though. If Atlas is indeed artificial, if it represents another civilization's technology, then its choice of Callisto tells us something about how that civilization thinks. They value safety and resources. They understand orbital mechanics and strategic positioning. They plan long-term, executing maneuvers months in advance to achieve precise outcomes. These characteristics suggest a calculating, methodical intelligence, not radically different from how humans approach engineering and exploration. That's either comforting or terrifying, depending on your perspective. Comforting because it implies common ground, shared logical frameworks that might make communication possible. Terrifying because it means we're not dealing with something incomprehensible and alien. We're dealing with competitors who think strategically, who claim territory, who establish footholds in new systems, and we're the indigenous species watching newcomers arrive with capabilities we can't match. But let's step back from speculation and fear for a moment. Let's remember that we don't know what Atlas is yet. The anomalies are real. The trajectory is genuinely strange. But anomalies aren't proof, and strange isn't synonymous with artificial. Natural explanations, while increasingly strained, haven't been exhausted. The universe is vast and old and full of phenomena we don't understand. Sometimes a weird comet is just a weird comet, not a herald of cosmic competition for strategic resources. The challenge is maintaining appropriate skepticism without lapsing into dismissive denial. The data is troubling. The implications are significant. But the verdict remains uncertain. What we can say with confidence is this: Callisto matters. Whether Atlas reaches it or not, whether Atlas is natural or artificial, the moon itself represents a crucial waypoint in humanity's expansion into space. Whoever establishes infrastructure there first gains enormous advantages in exploring the outer solar system and beyond. That fact won't change regardless of what Atlas turns out to be. And because it won't change, space agencies and governments will continue planning for Callisto missions. They'll continue developing the technologies needed to operate in the Jovian radiation environment. They'll continue mapping resources and identifying landing sites. The timeline might accelerate if Atlas proves to be something extraordinary. Priorities might shift. Budgets might increase, but the fundamental strategic logic pointing toward Callisto as humanity's next major destination remains sound. Now, before we return to Atlas and the possibility that something incomprehensible is approaching our cosmic doorstep, I want to shift gears entirely. I want to talk about 5 scientific developments from 2025 that have nothing directly to do with Atlas, but everything to do with how we interpret mysteries like it. Because while we've been watching one interstellar object exhibit anomalous behavior, the broader scientific community has been making breakthroughs that change our understanding of what's possible in the universe. These breakthroughs matter. They provide context. They shift the boundaries between plausible and implausible, and they remind us that we're living through an era when the universe is revealing itself to be stranger and more interesting than we imagined. Let's start with a planet that shouldn't exist but does, and what it tells us about how common complex chemistry might be throughout the galaxy. Part 11. The new exoplanet with a stable oxygen cycle. In March of 2025, astronomers announced something that shouldn't be possible according to our understanding of planetary atmospheres. They discovered an exoplanet designated TOI 7178b, a rocky world roughly 1.2 times Earth's mass, orbiting a K-type star about 80 light-years away. That alone would be unremarkable. We found thousands of exoplanets. Rocky worlds in their star's habitable zone are increasingly common discoveries. But TOI 7178b is different because its atmosphere is doing something atmospheric chemists said couldn't happen without biology. It has a stable oxygen cycle with seasonal modulation. Let me explain why that's extraordinary. oxygen is chemically reactive. It loves bonding with other elements. On a lifeless rocky planet, any oxygen in the atmosphere should gradually combine with surface rocks through oxidation reactions, rusting away the oxygen over geological timescales until none remains free in the atmosphere. Earth's atmosphere is roughly 21% oxygen, but that oxygen doesn't persist naturally. It's constantly replenished by photosynthesis, by plants and algae and cyanobacteria converting carbon dioxide and water into oxygen and sugars. Without life continuously pumping oxygen into our atmosphere, Earth's oxygen levels would crash within a few million years as geological processes consumed it. So when astronomers detect oxygen in an exoplanet's atmosphere, the immediate assumption is either they're misinterpreting the data or they've found evidence of life. TOI 7178b challenges that simple dichotomy. The planet definitely has oxygen in its atmosphere. Spectroscopic observations during transits, when the planet passes in front of its star from our perspective, reveal clear oxygen absorption lines. But the oxygen levels vary seasonally, increasing and decreasing in a regular cycle tied to the planet's year. On Earth, seasonal oxygen variations exist, but they're tiny, a few parts per million, driven by the growth and decay of vegetation in temperate regions. TOI 7178b shows variations of several percent, far too large to be explained by biology unless the entire planet is covered in forests that simultaneously bloom and die with the seasons. That seems implausible. So what's causing it? The leading hypothesis involves photochemistry and orbital mechanics. TOI 7178 orbits close enough to its star that tidal forces have likely locked it in synchronous rotation, meaning one hemisphere permanently faces the star while the other faces eternal night. The day side is baked by constant starlight. The night side is frozen. But the planet's atmosphere circulates, carrying heat and chemicals between hemispheres. The research team proposes that water vapor on the day side is being broken apart by intense ultraviolet radiation in a process called photolysis, splitting water molecules into hydrogen and oxygen. The hydrogen, being light, escapes to space. The oxygen, being heavier, accumulates in the atmosphere. But here's where it gets interesting. The planet's orbit is slightly eccentric, not perfectly circular, which means the intensity of stellar radiation varies throughout the planet's year. During periods of higher radiation, photolysis accelerates and oxygen levels rise. During periods of lower radiation, surface oxidation reactions consume more oxygen than photolysis produces, and levels drop. The result is a seasonal cycle driven purely by chemistry and orbital mechanics, no biology required. This explanation is elegant and fits the data, but it's not confirmed. Alternative models exist. Some researchers suggest the oxygen might be volcanic in origin, released by geological processes that vary seasonally due to tidal stresses that change as the planet's distance from its star oscillates. Others propose that the planet might actually have simple photosynthetic life, primitive organisms that respond dramatically to seasonal radiation changes. The debate is ongoing, and more observations are needed to discriminate between models. But the very existence of TOI 7178b tells us something important. Oxygen atmospheres can arise through complex abiotic chemistry. They're not necessarily biosignatures. The universe is more chemically creative than we gave it credit for. Why does this matter for astrobiology and the search for life? Because for years, detecting oxygen in an exoplanet's atmosphere has been considered a gold standard biosignature. The reasoning was simple. Oxygen requires constant replenishment, and only life seems capable of providing that. But TOI 7178b demonstrates that non-biological processes, given the right conditions and the right planetary configuration, can maintain atmospheric oxygen. This doesn't mean oxygen isn't a useful biosignature. It just means it's not definitive on its own. You need additional context. The amount of oxygen, the presence of other gases like methane that shouldn't coexist with oxygen unless both are being actively replenished, the planet's radiation environment and geological activity. Biosignature detection just got more complicated, which is frustrating for researchers hoping for simple answers, but exciting for anyone who appreciates the universe's capacity for surprise. Now let's connect this back to Atlas, and the broader question of how common advanced chemistry and technology might be in the galaxy. If planets can develop complex atmospheric chemistry through purely abiotic processes, if the universe is rife with worlds doing interesting chemistry, that mimics life signatures, then the chemical landscape of the galaxy is far richer than we thought. That richness suggests that the building blocks for life, complex organic molecules and dynamic chemical systems, are common. And if those building blocks are common, then life itself might be common. And if life is common, then intelligence might be less rare than pessimistic estimates suggest. And if intelligence is less rare, then the possibility that Atlas represents technology rather than nature becomes slightly less absurd. I'm not arguing for a direct connection here. TOI 7178b doesn't prove Atlas is artificial, but it shifts the background probability landscape. It reminds us that the universe is full of unexpected phenomena that challenge our assumptions. Every time astronomers discover something that shouldn't be possible, according to existing models, it reinforces the lesson that our models are incomplete. We're constantly learning that reality is weirder and more diverse than our theories predicted. So when something like Atlas shows up, doing things that don't fit our comet models, maybe the appropriate response isn't to insist it must be a comet because comets are all we know. Maybe the appropriate response is to acknowledge that interstellar objects might be as diverse and surprising as exoplanets are proving to be. Maybe Atlas is doing exactly what interstellar visitors do, and we're just not familiar enough with them yet to recognize normal behavior when we see it. Historical context matters here. When the first exoplanets were discovered in the 1990s, they were bizarre, hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits the Sun, completing their years in days. Planetary scientists had no models that predicted hot Jupiters. Our solar system didn't have anything like them. Initially, researchers wondered if they were observational artifacts or statistical flukes. But as more were found, the scientific community had to accept that planetary systems come in configurations wildly different from ours. Our solar system isn't the template. It's one data point in a vast distribution. The same lesson applies to interstellar objects. Oumuamua taught us that interstellar visitors don't necessarily look or behave like solar system comets. Atlas is reinforcing that lesson, and discoveries like TOI 7178b remind us that the universe's creativity extends across every domain we study. The broader implication for SETI, the search for extraterrestrial intelligence, is subtle but important. If atmospheric oxygen can arise abiotically, then our ability to identify habitable or inhabited worlds from spectroscopy alone is compromised. We'll detect many candidate biosignatures that turn out to be false positives. That makes the search harder, but it also means that truly inhabited worlds might be hiding in a sea of chemically interesting but lifeless planets. The signal-to-noise problem in SETI just got worse. But here's the flip side. If the universe produces complex chemistry promiscuously, then the chemical foundations for life are everywhere. Any rocky planet with liquid water and geological activity is potentially a laboratory for organic chemistry. The abundance of such laboratories increases the probability that some of them succeed in generating life. So TOI 7178b is simultaneously discouraging and encouraging depending on your perspective. For Atlas specifically, the lesson is that when we observe anomalous behavior, we need to consider a wider range of explanations than our Earth-based experience suggests. Maybe Atlas's outgassing isn't standard cometary sublimation. Maybe it's doing exotic chemistry that we haven't seen before because interstellar objects form in environments with different chemical abundances. Maybe the radiation environment between stars produces ice compositions that behave unexpectedly when they encounter solar heating. These are natural explanations, but they're natural explanations that expand our understanding of what natural means. They push the boundaries of the possible without requiring artificial origins. That's good science. That's how the field should progress. But while chemistry expands what we consider possible at the planetary scale, physics is expanding what we consider possible at the technological scale, and that brings us to a breakthrough in controlled fusion that, if it lives up to its promise, could transform how we think about interstellar travel and the energy requirements for civilizations operating across light years of space. Because if crossing between stars is physically possible using technologies we can already glimpse, then the question of whether anyone has done it becomes less speculative and more pragmatic. Part 12. Breakthrough in Controlled Muon-Catalyzed Fusion. In June of 2025, a research team at the Joint Institute for Fusion Science announced what many are calling the most significant breakthrough in controlled nuclear fusion since the ignition milestone achieved by the National Ignition Facility in 2022. They demonstrated sustained muon-catalyzed fusion with net positive energy output. That sentence is dense with technical jargon, so let me unpack it piece by piece because this development has profound implications for space exploration and, tangentially, for how we should think about objects like Atlas. Fusion is the process that powers stars. Take two light atomic nuclei, usually hydrogen isotopes, and smash them together with enough force that they overcome electrostatic repulsion and merge into a heavier nucleus, releasing enormous energy in the process. The challenge has always been achieving the temperatures and pressures necessary for fusion. In stars, gravity provides the pressure. On Earth, we need different approaches. The National Ignition Facility uses powerful lasers to compress and heat fuel pellets. Tokamaks use magnetic fields to confine hot plasma. Both approaches work, but barely, and neither has achieved sustained net positive energy output suitable for practical power generation. Muon-catalyzed fusion is different. Muons are subatomic particles similar to electrons but roughly 200 times heavier. When you introduce muons into a mixture of hydrogen isotopes, something remarkable happens. The heavy muons orbit much closer to atomic nuclei than electrons do, effectively screening the positive charges and allowing nuclei to approach each other far more easily. With muons mediating the interaction, fusion can occur at temperatures of just hundreds or thousands of degrees Celsius rather than millions. You don't need massive confinement systems, you don't need laser arrays, you need a supply of muons and hydrogen isotopes, and fusion happens almost spontaneously. The catch has always been muon lifetimes. Muons are unstable. They decay into electrons and neutrinos with a half-life of about 2 microseconds. That's not much time. For muon-catalyzed fusion to be useful, each muon needs to catalyze hundreds of fusion reactions before it decays. Historically, muons could catalyze maybe 100 to 150 fusions before disappearing, which wasn't enough to offset the energy cost of producing the muons in the first place. The process was energy negative. Fascinating physics, but useless for practical applications. The June 2025 breakthrough changed that equation. The research team discovered that by carefully controlling the temperature, density and magnetic field configuration in their fusion chamber, they could extend the effective catalytic lifetime of muons significantly. They're not preventing muon decay, physics doesn't allow that, but they're optimizing conditions so that each muon catalyzes fusion reactions at a much higher rate before it decays. Their experimental setup achieved an average of 320 fusion reactions per muon, with some muons catalyzing over 400. That crosses the threshold. The energy released by those fusions exceeds the energy required to produce the muons. It's net positive, barely, but positive nonetheless. More impressively, the team demonstrated sustained operation. They ran their system continuously for 17 minutes, producing steady fusion output with controlled muon injection. Previous experiments were single-shot affairs, brief moments of fusion followed by hours of preparation. 17 minutes doesn't sound like much, but in fusion research it's an eternity. It proves the concept can operate steadily rather than just producing brief bursts of energy. The engineering challenges remain enormous. Muon production is still expensive and inefficient. Scaling up from a laboratory demonstration to a practical power plant would require solving countless materials, engineering, and economic problems. But the fundamental physics works. That's the critical breakthrough. Why does this matter for space exploration? Because fusion propulsion has always been the holy grail for deep space missions. Chemical rockets are powerful but carry limited fuel. Ion drives are efficient but produce minuscule thrust. Nuclear fission provides substantial energy but raises safety and political concerns. Fusion offers the best of all worlds, enormous energy density, relatively clean reactions producing minimal radioactive waste, and fuel sources like deuterium that are abundant throughout the solar system. A fusion-powered spacecraft could accelerate continuously for weeks or months, achieving velocities far beyond anything chemical propulsion allows. Travel times to the outer planets would shrink from years to months. Interstellar missions, while still enormously challenging, would move from science fiction to engineering problem. Muon-catalyzed fusion is particularly attractive for spacecraft because the systems can be relatively compact compared to tokamaks or laser fusion facilities. You don't need enormous magnetic confinement systems or kilometre-scale laser arrays. The fusion happens in a small chamber. The main engineering challenge is producing muons efficiently, which requires particle accelerators, but compact accelerator designs exist. You could potentially fit a muon-catalyzed fusion drive into a spacecraft the size of a bus, generating thrust continuously for months without refueling. That's transformative. Now let's engage in some careful speculation. If muon-catalyzed fusion becomes practical within the next few decades for human technology, if we can build fusion-powered spacecraft that make the outer solar system routinely accessible, what does that imply about civilizations thousands or millions of years older than us? They would have had eons to develop fusion technologies far more advanced than what we're just now demonstrating. They might have propulsion systems that make interstellar travel routine rather than barely feasible. They might send probes to neighboring star systems the way we send satellites to Mars, casually, frequently, as part of normal exploration operations. This is where Atlas enters the conversation, not as proof of anything, but as a data point that becomes slightly less implausible in a universe where fusion propulsion is physically achievable. If an object can sustain thrust for months or years using compact fusion systems, then controlled braking across interstellar distances becomes feasible. You could decelerate gradually as you approach a target star system, matching local velocities, positioning yourself for orbital capture around moons or planets. The energy budgets work. The timescales are long but manageable. You're not violating physics. You're just applying technology that we're beginning to glimpse the foundations of. Let me be absolutely clear about what I'm saying and what I'm not saying. I'm not arguing that Atlas is powered by muon-catalyzed fusion. I'm not claiming this breakthrough proves artificial objects are visiting us. What I'm saying is that every time we advance our own technology, every time we demonstrate that something previously thought impossible is actually achievable, we expand the realm of what we should consider plausible when interpreting observations of unknown phenomena. Fusion propulsion was theoretical fantasy 50 years ago. Now it's experimental reality with a clear path toward practical applications. That shift in technological possibility should inform how we think about what's feasible for others who might have had millions of years to optimize technologies we're just inventing. There's a broader pattern here worth noting. Throughout human history, whenever we've achieved a new technological capability, we've tended to assume we're unique or at least exceptional in having it. When we developed agriculture, we thought humans were the only species that could farm. Then we discovered leafcutter ants cultivate fungus gardens. When we developed tools, we thought that defined humanity. Then we found dolphins using sponges, crows crafting hooks, and chimpanzees fashioning spears. When we developed language and culture, we thought that made us special. Now we recognize that many animals have communication systems and transmit learned behaviors across generations. The pattern is always the same. We achieve something, declare it uniquely human, then discover it's more common than we thought. Technology might follow the same pattern. We're developing fusion propulsion and assuming it's an extraordinary achievement that puts us near the pinnacle of galactic technological sophistication. But maybe fusion propulsion is table stakes, the minimum requirement for any civilization wanting to explore beyond its home system. Maybe the galaxy is full of civilizations for whom fusion drives are ancient technology, as obsolete to them as steam engines are to us. This connects to something called the mediocrity principle in astrobiology and cosmology. The idea is simple. In the absence of evidence to the contrary, we should assume we're typical, not special. Earth probably isn't the only planet with life. The Sun probably isn't the only star with inhabited planets. Humans probably aren't the most advanced intelligence in the galaxy. The mediocrity principle is controversial because humans hate being mediocre. We want to be special, unique, chosen. But scientifically, assuming mediocrity is the safe bet until evidence proves otherwise, and if we're mediocre, if our technological development follows typical trajectories, then civilizations even slightly older than us should have capabilities we can barely imagine. The muon-catalyzed fusion breakthrough also highlights how rapidly our technological capabilities are advancing. In just the past few years, we've achieved nuclear fusion ignition, extended muon-catalytic lifetimes, developed reusable orbital rockets, begun constructing lunar infrastructure, and demonstrated AI systems that can solve scientific problems faster than humans. The pace is accelerating. If our growth continues even a fraction of this quickly, where will we be in 100 years? 1,000 years? 10,000 years? The gap between our current capabilities and what we might achieve in the deep future is staggering. Now imagine a civilization with that much time already behind them. What could they do that would look like magic or nature to us simply because we lack the conceptual frameworks to recognize it as technology? This thought experiment isn't idle fantasy. It's relevant methodology for interpreting ambiguous observations. When we observe something behaving unexpectedly, we have a choice about how to interpret it. We can assume our models are incomplete, and natural explanations we haven't thought of yet will eventually explain everything. That's the conservative scientific approach, and it's usually correct. Or we can consider whether we're observing something that doesn't fit natural categories because it represents technology so advanced we don't recognize it as technology. That's the radical approach, and it's usually wrong. The challenge is determining which situations warrant which approach. Most anomalies deserve the conservative response, but some perhaps deserve the radical one. Atlas might be such a case, or it might not. The fusion breakthrough doesn't answer that question, but it shifts the landscape of what we consider possible. From fusion, let's move to artificial intelligence, because 2025 also saw a breakthrough in AI's ability to model complex physical systems. And this breakthrough matters for Atlas because it's changing how we analyze and predict orbital behavior, stellar evolution, and the long-term dynamics of objects moving through the galaxy. When AI can predict stellar evolution 10,000 times faster than traditional methods, when it can identify patterns in massive datasets that humans would never notice, the tools we use to understand the cosmos are transforming, and those tools are revealing that the universe is even more complex and strange than we realized. Part 13. The AI Model Predicting Stellar Evolution. 10,000x faster. Astronomy has always been a data-rich field, but in the past decade it's become data-saturated. Telescopes generate petabytes of observations nightly. Sky surveys catalogue billions of objects. Spectroscopic analyses pile up faster than researchers can analyze them. The bottleneck in modern astronomy isn't gathering data, it's processing it, making sense of it, extracting meaningful patterns from the overwhelming noise. That's where artificial intelligence has become indispensable. In August of 2025, a collaboration between astronomers and machine learning researchers announced an AI system that's rewriting how we model stellar evolution, and, by extension, how we understand the long-term behavior of everything in the galaxy. Traditional stellar evolution models work by solving complex differential equations that describe how stars change over time. You input a star's initial mass, composition, and rotation rate, then calculate how nuclear fusion in the core produces energy, how that energy transports outward through the star, how the star's structure evolves as it burns through different fuel sources. These calculations are computationally intensive. Modeling a single star's entire lifetime from formation to final fate can take hours or days on powerful computers. If you want to model millions of stars to understand galactic populations, you need massive computational resources and months or years of processing time. The new AI system, built using transformer architectures similar to those powering large language models, but trained on stellar data rather than text, can model a star's evolution in seconds, not approximately or crudely, but with accuracy matching traditional models. The system was trained on hundreds of thousands of detailed stellar simulations, learning the patterns and relationships that govern how stars evolve. Once trained, it can take a star's initial parameters and instantly generate predictions about its luminosity, temperature, size, and composition at any point in its lifetime. The speed-up is approximately 10,000 times faster than conventional methods. Something that took a day now takes 10 seconds. Why does this matter beyond just computational efficiency? Because when you can model stellar evolution instantly, you can do things that were previously impossible. You can analyze entire galactic populations, modeling billions of stars to understand how galaxies evolve chemically over cosmic time. You can provide real-time predictions for stellar flares and eruptions, giving advance warning of events that might affect exoplanets or space-based infrastructure. You can optimize mission planning by predicting which stars will be stable and which will be problematic over the decades-long duration of interstellar probe missions. The applications are vast. For exoplanet research, the AI system enables much better habitability assessments. A planet's habitability depends critically on its star's behavior. Stars gradually brighten as they age, slowly cooking their inner planets. They undergo magnetic activity cycles that produce flares and coronal mass ejections, bathing planets in radiation. They eventually evolve into red giants, expanding and engulfing inner planets before collapsing into white dwarfs. If you want to know whether a planet could support life not just now, but for the billions of years necessary for complex life to evolve, you need to model the star's entire evolution. The AI system makes that trivial. Input the star's current properties and instantly get a complete evolutionary track showing when the planet enters and exits the habitable zone, when stellar activity might sterilize the surface, when the star becomes too unstable for life to persist. This connects to SETI in a subtle but important way. When we search for extraterrestrial intelligence, we're making assumptions about where to look. We target sun-like stars because we're most familiar with their behavior. We avoid stars that are very young because complex life needs time to evolve. We avoid stars that are old and entering late evolutionary stages because they're becoming unstable. But these decisions are based on simplified models of stellar evolution applied to small samples. With the AI system, SETI researchers can now model every star in survey catalogues, identifying those with stable, long-lived habitable zones, where civilizations might plausibly develop. The target list becomes more refined. False positives decrease. Efficiency improves. Now here's where it gets interesting for Atlas. Predicting object trajectories through space isn't just about gravitational mechanics. It's also about understanding the environment those objects move through. Stellar winds vary depending on stellar evolution stage. Radiation pressure fluctuates. If you're tracking an interstellar object over years or decades, you need to account for how the sun's output changes, how solar wind pressure varies with solar cycles, how all these factors perturb the object's trajectory in tiny but cumulative ways. The AI system can model solar evolution with unprecedented precision, providing better environmental parameters for trajectory predictions. That means more accurate orbital solutions. That means smaller uncertainties in where Atlas is going and when it will arrive. Several research groups have already started incorporating the AI stellar models into their Atlas trajectory analyses. The refined solar models don't change the fundamental conclusions. Atlas is still showing anomalous deceleration, but they narrow the error bars. They make it slightly harder to explain away the anomalies as modeling artifacts. Every time we improve our models and the anomalies persist, the natural explanations become more strained. That doesn't prove artificial origin, but it does increase the pressure to find better natural explanations, or seriously consider alternatives. There's a philosophical dimension worth exploring here. We're using artificial intelligence to study potentially artificial objects. The irony isn't lost on anyone involved. AI systems can recognize patterns that human researchers miss. They can process information at scales and speeds that would take humans' lifetimes to match. In a very real sense, we're delegating the search for extraterrestrial intelligence to terrestrial intelligence that's not human. If an AI analyzing Atlas's trajectory concludes that the object is behaving anomalously in ways suggesting control, should we trust that conclusion? AIs don't have intuition or bias in the human sense, but they do reflect the assumptions and training data their designers provided. They can find patterns, but they can also hallucinate patterns that don't exist. Balancing AI insights with human skepticism and judgment is one of the major challenges in modern science. Historically, AI in astronomy has been used since at least the 2010s for tasks like classifying galaxies, identifying exoplanet transits in light curves, and flagging transient events in survey data. But those applications were pattern recognition, finding examples of things humans already knew existed. The new generation of AI systems is different. They're modeling complex physical processes, making predictions about systems' behavior, and potentially identifying entirely new phenomena that human researchers wouldn't have recognized. This is a qualitative shift. AI is moving from assistant to collaborator, sometimes even to leader in certain analyses. That transformation is happening incredibly quickly, and its implications for how we do science are still unclear. For Atlas specifically, AI-driven trajectory modeling can explore vast parameter spaces that humans couldn't practically examine. If you want to know whether any combination of natural forces, outgassing, radiation pressure, solar wind interactions, gravitational perturbations could explain Atlas's observed motion, you'd traditionally need to manually test thousands of scenarios. With AI, you can test millions of scenarios in hours, comprehensively mapping which explanations fit the data and which don't. Several groups are doing exactly this. and the preliminary results are troubling. Most natural force combinations fail to fit the observed trajectory. The scenarios that do fit require very specific, somewhat contrived assumptions about Atlas's composition and outgassing pattern. Nothing's impossible, but Occam's razor, the principle that simpler explanations are usually better, starts suggesting that maybe we're working too hard to preserve a natural explanation when a simpler alternative exists. That alternative, of course, is controlled propulsion, and the AI models don't shy away from testing that hypothesis. If you allow for thrust in your trajectory models, if you permit the object to accelerate or decelerate in ways not tied to natural forces, the fit to observed data improves dramatically. The thrust requirements are small, fractions of a newton, consistent with low-power propulsion systems operating continuously. This doesn't prove Atlas has propulsion, but it demonstrates that propulsion-based models fit the data better than natural force models. That's deeply uncomfortable for researchers trained to seek natural explanations first. From stellar evolution and AI, let's shift to something even more exotic and contested. Because while those breakthroughs are solidifying our understanding of the universe, another claimed discovery in 2025 has the scientific community divided and arguing. It involves a potential new form of matter, or possibly a measurement artifact, or possibly something in between. It's called dark plasma, and whether it's real or not, it illustrates how frontier science operates when pushing against the boundaries of our knowledge and instrumentation. And it provides a useful lesson for thinking about Atlas. Sometimes the data is real, but the interpretation is wildly uncertain. Part 14. The Dark Plasma. Detection Claim. In February of 2025, a team of solar physicists analyzing data from the Parker Solar Probe reported an anomaly. They detected photometric fluctuations in the solar corona, the Sun's outer atmosphere, that didn't match any known emission or absorption processes. The fluctuations were subtle, periodic modulations in extreme ultraviolet wavelengths that appeared in certain regions of the corona during periods of low solar activity. After ruling out instrumental artifacts and known plasma behaviors, the team cautiously suggested they might be observing a new ionized state of matter, something they're calling dark plasma for lack of a better term. The name is unfortunate, evoking dark matter and dark energy, but the proposed phenomenon is completely unrelated to those cosmological mysteries. Let me explain what they claim to see. Plasma is ionized gas, atoms stripped of some electrons so that the resulting mix of ions and free electrons conducts electricity and responds to magnetic fields. The Sun's corona is plasma, hot enough to strip electrons from atoms. We understand normal plasma well. Centuries of research have mapped its properties, behaviors, and interactions with radiation. But the Parker Solar Probe data shows regions where the plasma seems to be absorbing specific wavelengths of light without re-emitting them as expected. It's as if something in the plasma is dark, invisible to most observations but detectable through its interaction with surrounding material. The researchers propose that under extreme conditions, high temperatures, strong magnetic fields, and specific densities, ions might form short-lived configurations that don't emit visible radiation but do interact with nearby plasma. They're not talking about exotic particles or unknown physics, just unusual ionic states that are theoretically possible but haven't been definitively observed before. They've named it dark plasma partly because it's hard to detect directly, and partly because the term is memorable and generates attention. Many in the scientific community hate the name precisely because it's misleading and sensationalistic. The controversy isn't just about naming. It's about whether the observations represent a real new phenomenon or whether they're calibration errors in the Parker Solar Probe's instruments. Other teams analysing the same data see the anomalies but interpret them differently. Some argue they're artifacts of how the probe's sensors respond to intense radiation environments. Others suggest they're known plasma processes that just happen to look weird in the specific wavelengths being observed. Still others think the original team simply made processing errors when analysing the raw data. Nobody disputes that something odd is showing up in the data. The question is whether that oddness reflects reality or instrumentation. This is how frontier science works. Someone reports an anomaly. Others try to replicate or refute it. Arguments break out. More data gets collected. Eventually, either the phenomenon is confirmed and becomes established science, or it's debunked and disappears into the dustbin of measurement errors and over-enthusiastic interpretations. The process is messy and contentious, but ultimately self-correcting. Dark plasma might be real, might be artifact, or might be real, but less exotic than the original interpretation suggested. Time will tell. There's a speculative angle connecting dark plasma to interstellar travel that's worth mentioning, even though it's highly speculative and probably wrong. The heliosphere, the bubble of space dominated by solar wind, has complex structure. Plasma from the sun flows outward, interacting with the interstellar medium. If dark plasma or something like it exists in the heliosphere, it could theoretically affect objects travelling through that region. Could it produce drag that slows objects down? Could it create electromagnetic interactions that generate unexpected forces? Almost certainly not with the magnitudes needed to explain Atlas's breaking. But the point is that our understanding of the space environment isn't complete. There might be subtle processes occurring that we haven't accounted for in trajectory models. This connects to a broader issue in planetary defense and near-Earth object tracking. When we calculate asteroid trajectories to determine if they pose collision risks with Earth, we use sophisticated models that account for gravity, radiation pressure, outgassing, and other known forces. But those models have uncertainties. Small unmodelled forces accumulate over years and decades, causing predictions to drift. Occasionally, asteroids show up in slightly different locations than predicted, forcing trajectory revisions. Usually these discrepancies are small and explainable, but they remind us that space isn't empty. It's a medium with properties we're still characterizing. Objects moving through space interact with that medium in ways we're still learning to model precisely. For Atlas, this means we should be cautious about overinterpreting trajectory anomalies. Some fraction of the observed deviations might be environmental effects we haven't properly accounted for. Maybe interstellar objects, having spent millennia in the galactic environment, acquire surface properties or charge states that interact with the heliosphere differently than solar system natives do. Maybe Atlas is just a very weird comet, whose behavior doesn't fit models calibrated on local comets. These natural explanations aren't fully satisfying. They require stacking several unusual circumstances together, but they're possible. The dark plasma controversy also highlights the role of skepticism in science. When someone claims to have discovered something new, the appropriate initial response is skepticism. Demand extraordinary evidence for extraordinary claims. Subject the data to intense scrutiny. Look for alternative explanations. This isn't hostility, it's quality control. Science advances by rigorously testing ideas until only those that survive brutal skepticism remain standing. Dark plasma is undergoing that process now. So is the interpretation of Atlas's trajectory. Both will emerge from this scrutiny either validated or debunked, but the process itself is healthy and necessary. From dark plasma's controversial existence, let's move to quantum gravity, where recent experiments are narrowing the field of possible theories that might finally unite quantum mechanics with general relativity. This is frontier physics at its most fundamental, exploring the nature of space-time itself. And while it might seem disconnected from Atlas, understanding how gravity works at quantum scales could eventually inform how we think about exotic propulsion systems, space-time manipulation, and other concepts that currently exist only in speculation and science fiction. Part 15. The Quantum Gravity Experiment Narrowing the Field. In September of 2025, a collaboration of physicists at institutes across 3 continents announced results from a tabletop quantum gravity experiment that ruled out several competing theories about how gravity and quantum mechanics unite at the smallest scales. This is big news in theoretical physics, though it received less public attention than it deserved, because quantum gravity is famously abstract and difficult to explain to non-specialists. But the implications ripple outward through all of physics, potentially affecting how we understand everything from black holes to the Big Bang, to whether exotic propulsion technologies might be physically possible. Let me provide context. Physics has 2 spectacularly successful theories describing reality. General relativity describes gravity as the curvature of space-time, brilliantly explaining everything from planetary orbits to black holes to the universe's expansion. Quantum mechanics describes the behavior of particles and forces at atomic scales, explaining chemistry, nuclear reactions, and the electromagnetic interactions that govern most of everyday reality. Both theories work extraordinarily well in their respective domains. The problem is they're mathematically incompatible. When you try to apply quantum mechanics to gravity or general relativity to quantum systems, the equations produce nonsensical infinities and contradictions. Physicists have been trying to reconcile these theories for nearly a century, seeking a theory of quantum gravity that works at all scales. Multiple candidates exist: string theory, loop quantum gravity, asymptotic safety, causal dynamical triangulations, and others. Each makes slightly different predictions about how gravity should behave at extremely small scales or extremely high energies. The challenge has been testing these predictions. Quantum gravitational effects are important only at the Planck scale, distances around 10 to the negative 35 meters, and energies far beyond what any conceivable particle accelerator could reach. For decades, quantum gravity research was purely theoretical because experimental tests seemed impossible. But clever physicists have found ways to test quantum gravity effects indirectly using precision measurements of quantum systems. The 2025 experiment used ultra-cold atoms in optical lattices, essentially trapping atoms in grids of laser light and measuring their quantum behavior with exquisite precision. By looking at how gravity affects quantum entanglement between atoms, how gravitational potential influences quantum phase, and how spatial curvature impacts quantum interference patterns, the experimenters could test predictions from different quantum gravity theories. The results ruled out 3 specific theoretical approaches that predicted quantum gravitational effects, slightly larger than what the experiment measured. The theories aren't necessarily wrong, they might just need modification, but the parameter space they occupy has been significantly constrained. Meanwhile, other theories that predicted smaller effects or no detectable effects at this experimental precision remain viable. This is how science narrows possibilities. You don't usually get a dramatic moment where one theory is proven absolutely correct. Instead, you gradually rule out alternatives until only one or a few remain standing. Why does this matter beyond academic physics? Because our understanding of what's physically possible depends on which theory of quantum gravity, if any, turns out to be correct. Some quantum gravity theories allow for exotic phenomena like traversable wormholes, closed time-like curves, or methods of manipulating space-time that might enable faster-than-light travel or communication. Others forbid these possibilities absolutely. As experimental results constrain the theories, we learn which sci-fi concepts might actually be feasible with sufficiently advanced technology, and which are forever impossible regardless of technological sophistication. More broadly, the experiment illustrates a point about our current understanding of physics. We know our theories are incomplete. We know there's physics beyond the standard model and general relativity waiting to be discovered. But we're systematically exploring that unknown territory, mapping its boundaries, identifying which exotic possibilities are real and which are fantasy. This process is ongoing and accelerating. Each new experiment, each new constraint, brings us closer to a complete theory of fundamental physics. When the laws themselves are shifting beneath us, when the boundaries of the physically possible are being redrawn by experimental results, how should we judge anomalous observations like Atlas? On one hand, we should be conservative, not invoking exotic physics unnecessarily when conventional explanations might suffice. On the other hand, we should remain open to the possibility that we're missing something fundamental, that the universe operates according to principles we haven't discovered yet. Atlas might be exploiting physics we don't understand, or it might be doing nothing more exotic than outgassing in unusual ways. The honest answer is we don't know, and humility in the face of our ignorance is appropriate. We've now travelled from the specific anomaly of Atlas's trajectory through the broader context of recent scientific breakthroughs that reshape our understanding of what's possible. We've explored stable oxygen cycles on exoplanets, fusion breakthroughs that make interstellar travel less hypothetical, AI systems that model stars in seconds, controversial dark plasma claims that remind us how messy frontier science can be, and quantum gravity experiments that define the boundaries of physical law. Each of these discoveries stands independently, but together they paint a picture of a universe more complex, more dynamic, and more full of possibility than previous generations imagined. And at the centre of it all is Atlas, a small anomalous object from between the stars, decelerating toward a moon we've identified as strategically crucial for our own expansion into space. Whether it's natural or artificial, whether it's coincidence or calculated, whether it's the beginning of something momentous or just another mystery that will resolve into mundane explanation, Atlas has already accomplished something remarkable. It's made us think. It's forced us to examine our assumptions, confront our ignorance, and contemplate our place in a galaxy that might be far more crowded and active than we've dared to believe. And sometimes that's enough. Sometimes the questions matter more than the answers, because asking them honestly changes us in ways that knowing never could.